brute force approach. So this is about the brute force approach, and this is the situation. Okay, for solving this problem, we can use the brute force approach. So the disadvantage of the brute force approach. This is the state space graph of the problem. Okay, state space graph or state space tree. This is the state space tree of problem, and then we should create the full state space. Okay, that's the problem. Okay, and you want to search the entire state space tree to get a solution or to find all solution. So this is a complex process as and the value of the input n increases. Okay, so to solve the problem we are using which approach? Backtrack approach. Okay, so what is backtrack approach? The state space tree. Okay, so what is state space tree? This is the state space tree of the problem. This is the state space tree of this problem. Okay, so you can observe for each problem there will different state space graphs will be there. Okay, so anyway, this is the state of this particular problem. Okay, so the basic idea is the state space tree is created in a controlled way using a bounding function. Okay, we will use the bounding function to control the growth of the tree. Okay, so what is bounding function means? Which is the bounding function? This is p. Okay, p is the bounding function. Okay, p actually the constraint in the problem is the bounding function. Okay, the constraint involved in the problem is the bounding function, or it is p. Okay, p. So using this p, we will control the growth of the state space tree. That is the approach used in backtrack approach. Okay. So this is one example of this is the example of solving problem. This same problem using backtrack approach. Okay. So you can observe here what we are doing is that I'll just draw it here. Okay, so we from the initial state. Okay, this is the initial state. We will start from there. Then this is our solution vector. I'm just drawing the solution vector here. I'm just drawing the solution vector here. There are three variables. There are three. This is a solution vector x. Okay, this is the solution vector x, and the solution vector x contains three positions. In this case, this is x of 0, this is x of 1, this is x of 2. We want to find the values here. Okay, we can fill the values with which are the values we can use to fill this dot. This is b1, b2, and g1. We can use that values. Okay, so basically, if you think about this, then we can. There are three values: b1, b2, and 2 boys and 1 girl. These are the values taken by xi. Xi can take value, this position take value, any of these three. This position will take these three. This position will take any of these three. Okay, so we from the initial state, and first we will fill this position. Okay, this position with B1. Okay, so this is filled with the B1. Okay, so that is we reaches the next state. Okay, then after reaching the next state, what we will do? We will check the constraint. uh, Check the constraint. Okay, we will constraint. Uh, for example, we reached here. uh, We reached here. Then we will check whether this solution up to this point, whether the solution is acceptable or not. That is, we started from here, then we enter a value v1 here, then we reach at the next state. Then before going to the next state, what we will do? We will check this solution is okay or not using a constraint function. This is okay. Okay, no problem. Which is the constraint? G should not be come here. This is the only constraint involved in this problem. Okay. G is not allowed here. That is, in this case, only one constraint is there. That is, the middle position should not contain G. Okay, G1. G1 should not be here. This is the only constraint. So, we filled B1 here. B1 here. Then we moved to the next state here. After reaching here, what we will do? We will check whether our previous solution is acceptable or not. Okay, using the constraint. So this is okay. Next, what we will do? From next, we will enter B2. Okay, next we will enter B2. Next, we are entering B2. Okay. Next, we entered B2. Okay. B2. Next, we enter B2 here. Okay. So, after entering B2, we will reach at this state. Okay. We reached at this state. We reached at this state. Then, before creating the next state, going to the next state, what we will do? We will check whether the solution up to this point, solution to this B1 and B2 is satisfying the constraint or not using P. That is, we will use the function constraint function P and check B1 and B2. Okay, B1, B2. If it is okay, if it is satisfying, then what I will do? I will enter G1 and go to this state. Okay, this is the concept you should understand. Okay, so I will repeat one more time. So I will enter G1 here. So this is the basic process involved in backtracking. So just try to understand the concept. So, I will repeat one more time. Okay. So okay. Initially, this is the situation. And we will enter here. Okay, initially we will enter B1 here. then it is at the position x0, 0th position. This is the solution vector x. This is the solution vector x. Okay, we entered B1. Then we go to the next stage here. Okay, we entered B1, then reach here. Then what we will do? Before going to the next state, check whether the solution up to this point is okay or not using P. Okay. If it is okay, we will proceed. Else we will stop. Okay. In this case, it is okay. So what we have done, we moved from here to here. Okay. That is we enter B2. Okay. We entered B2. We entered B2. Okay. Now we reached at which state? We reached here. Okay. We reached here. Then before going to the next state, okay, now we want to here. Okay, before going to the next state, that is before entering G1 here, what we will do? We will check that the solution up to this point, okay, whether the solution up to this point from P of B1, B2 satisfying the constraint or not. It is satisfying because our constraint is G1 should not be at the middle. Okay, so it is satisfying. So what we will enter G1. We will enter G1. So solution basically. Okay, this is a solution. Now we reached at the root. Okay, now we reached at the root. So this process is completed. This path from the root we start, then we applied all, then we reached at the leaf node. Okay, so that is completed. Next, what we will do? Next, what we will do? Please. ഹലോ, നിങ്ങളുടെ കണക്ഷൻ പോയിരുന്നു. എപ്പോഴാണ് സ്റ്റാർട്ട് ആയത് കേൾക്കാം? അനക ആരെങ്കിലും പെട്ടെന്ന് കണക്ഷൻ പോയിന്നായിരുന്നോ? ഓക്കെ ഓക്കെ. അപ്പോൾ so please try to understand this concept. So we created this path in the tree. Okay, next what we will do, we will go back, we will return back to this point. Then we from here we will try another alternatives. Okay, for example, you can note here it is completed. Here I can do this. Okay, now what we will do, okay, next എന്തായിരിക്കും ചെയ്യാൻ? നെക്സ്റ്റ് നമ്മൾ ഇവിടെ വീണ്ടും backtrack ചെയ്ത് ഈ പോയിന്റിലെത്തും. Then we will reach back at this point. Then we will try another alternative. Okay, B1 is already filled. Okay, B1 is already filled. That is, we will try to find out another solution. This is one solution. This is okay. Next, we will backtrack to this point and we will try to apply, try to find out another solution. So B1 is already here. Then what we will do? From this, we try to move to this. Okay. From this, we try to create. We try G1. Okay. We will add G1. So you can note here in the solution vector B1 is already there. Okay, B1 is already there. Then before adding G1, what we will check? We will check up to this point. Okay, up to this point. Before adding G1, I will check the solution up to this path. It is satisfying. Okay, so what I will do? I will add a G1. Now I added. Okay. Next, what will happen? Next, from this, what I will try, you can observe here. Now I reached at this state. Okay. Now I reached at this state. This is the current state. From that state, I will try to add which one? B2. I will try to add B2 here. Okay. I will try to add B2 here. But before adding B2, what I will do? Before adding B2, I will check the solution path from here to here. Up to this solution path I will check. Okay. Before, you can please observe, before adding B2, before adding B2, what I will do? I will check the solution path from this solution path. Okay, B1 G1. Okay, you can note here this solution path. Is it satisfying our constraint? No. Why? Because our constraint saying is that there should not be a girl in the second position. But here girl appears. So this will not be a solution. I will not add G1 to this state. Okay. You can observe here. Here I stop my expansion. Okay. From this node, I will not add B2 here. B2 is not added here. Okay. You can observe here. This is the advantage of backtracking. That is, B2 is not added here. Okay. We stopped the process here. Okay. We stopped the process here. So this is the advantage of backtracking approach. That is, before adding next node, we will check the solution up to this point is okay or not. If it is okay, I will add. Okay, else what I will do? I will terminate from that point. Now you can observe. Now you can observe. This is the situation. Okay. Now this is the situation. So here you can note a bound function is applied here and stopped the growth of the tree in this path. What is bound function? Bound function is actually P. Okay, P. P is our bound function or constraint function. It checks the constraint up to this point. Okay. Then it is not satisfied, then I stop it here. Then what I will do? I will go back. This is also, these two completed. I will return back. I reached back here. Then from that, what I will do? Here, this path is completed. All processes. Next, I will try another alternative, B2. Okay. So what I will do? Okay. Next, I will add B. Okay, I will add B2 to the solution vector. Then check. Then I reached at this point. From here, I will check whether previous added solution is feasible or not. It is okay. B2 can appear at the first position. Then I will move to this point. Okay. Then I entered B1. Reached here. From there, what I will do? I will check whether before adding G1. Okay. From this point, from this point, I will check whether the from the this node, from this point to the root or not. It is feasible or it is satisfying the constraint. So what I will do? I will add G1. Okay, I will add G1. The process is completed. I will add G1 and I reach the leave mode. So this is also a solution path. Okay, this is also a solution path. Then what I will do? Is there, okay, in the solution vector B there. Then from this I tried to add G1. Okay, from this I tried to add G1. Hello. Okay. Okay, from this I tried to add G1. So before adding G1, I will check the previous. So you can imagine I am here. Before adding G1, I will check the solution up to this point is okay or not. This is okay. So I will add G1. Then I reach at this. Okay, I reached at this state. But from this state, now I reached here. Before adding the next one to the solution vector, I will check the solution up to this point. No, because using an evaluation function, I will check this. But here G1 coming, okay, in the second position. So this is not a solution. I will terminate here. Okay, you can observe I terminated here. I will not further explore this path. Okay. That's the process. Next, what I will do again, go back to the root. Then I will explore this path. Okay, I will add a G1. Okay, after adding G1, so this is a false path. So then again I will start from the initial situation. Add G1 at the first position. Then add G1 to the first position. Then I will reach here from this solution. I reached here. Before I add to the next, I will check the solution up to this point is okay. It's okay. So I will add this one. I reach here. Then from here, before adding next node, I will check the solution up to this is okay. Okay. So I will add. So this is also okay. This is the solution path. Next, I will return back here. Then I will add B2. I reach here. From here, I will check whether before adding the next one, I will check the solution path up to this is okay. Okay, so add this one. So this is the state space graph. I explored all the paths, and here I terminated. Here also I terminated. Okay. So In this way, the state space tree is created. Okay, this way, the state space tree is created. The state space tree is created. So you can observe this is the state space tree created using backtrack approach. Using the backtrack approach, this is the state space tree created, and here you can note this here I terminated. Also here also I terminated. Okay. Remaining are solution path. This is a solution path. And this is a solution path. Then the solution path. Similarly, this is a solution path. There are 4 solution paths. Okay. So the advantage is you can observe here. Here this is the brute force state space tree. It contains more nodes or more bits than this approach. Okay, that is the real advantage of backtrack approach. That is, it will reduce the number of states in the state space tree. So, as a result, we will get a solution in a faster way. Okay, that is the advantage of using backtrack. This is the working of the backtrack approach. Okay. So it is very simple. Just try to understand this concept. Okay. Suppose I will repeat one more time. The basic thing involved in this is, suppose I reached at this point. Okay. Before adding the next state to the space graph, what I will do, I will check this to the root. Okay. It is evaluated using P. It is evaluated using the P. What is P? P is the constraint function or bounding function. If it is, you can bounding function. If it is okay, this path is okay, then I will add. Then I will proceed further. Okay. Then I will proceed further. If it is not okay, what I will do? I will stop here. Okay. So as a result, what will happen? The number of states is reduced. Okay. You can observe this one and this one. Brute force approach state space diagram and this state space diagram. Okay. This is the case of n equal to 3 only. Okay. This is the case n equal to 3. And if the n become large, there will be a significant advantage. Okay. There will be significant advantage. Okay. There will be a great reduction of number of states. Okay. So that is about this approach, and this is the advantage. So now I'm going to the terminologies. Okay, some terminologies. Okay, so okay. So now I'm going to the terminologies. Just simple. This is our state space graph. Okay. Using backtrack approach, we will always solve the problem like this. That is, we will try to create the state space graph, and from that graph we will find the solutions. So state space graph, there are some terminologies. One is the problem state. What is meant by problem state? Each node in the state space graph or state space tree is called a problem state. Okay, problem state. What is state space? All path from root to other node. Okay, what is state space means? State space means all path from root to other node. Okay, you can observe here all path, this path, this path. There are 6 paths there. Okay, in this case 6 paths there. So what is solution state? What is solution state mean? Problem state is for which the path from root to S is a solution. Okay, what is solution state means? For example, this is a solution state. Why? From this position to the root, this path defines a solution. This is a solution state. This is a solution state. Okay. Similarly, solution state. Okay. Similarly, this is a solution state. Okay. Similarly, this is a solution state. There are four solution states. Okay. So that's about the solution state. And next is the answer state. What is answer state? Solution state is for which the path from root to S defines a tuple that is a member of set of solution. It satisfies the implicit concept of the problem. Anyway, the same concept. What is answer state means? Solution state. Okay. From it forms a solution. That's all the constraint. Next is state space tree, organization of solution space. So this is actually this whole thing constitute this tree is called a state space tree. Okay. In the artificial intelligence next set you want to study this type of concept. So for solving some complicated gaming problems, you want to create this approach. You want to use this approach. Okay. State space approach. Next, state space tree. Then I'm defining another term, live node. Okay, what is live node mean? A node which has been generated and all of it have not yet been generated. Okay, that is live node. The node. E node means the live node whose children are currently being is called E node, and dead node. What is a dead node? A dead node is a generated node which is not to be expanded further, or all of it have been generated. For example, if you observe here, this is a dead node. Okay, this is a dead node. Okay, you can consider dead node. Okay, so this is about the terminologies used in the state space tree. Okay. Next, what I'm trying to do is now we familiarized with the state space tree and how can create the state space tree and some terminologies. Okay. In this is the most important terminology, answer state, because we want to use this in our algorithm. Okay. This is our backtrack based approach algorithm. Here we want to use that state term. Okay, we want to use the terminology answer state. Okay. So you need an idea about answer state, and from the exam point of view, sometimes they may ask some terminology. So please study this topic in that view also. Next, so this is about the backtrack approach, and so. And going back to this point, so the basic idea is to build up the solution vector one component at a time and use the modified criterion function to test whether the vector being formed has any chance to success. If there is a chance, it will proceed. This is the our backtrack approach. Then here there are constraints to be satisfied. Already I told, if you consider a problem, there are constraints. Which type of constraints we can consider? I think sometimes in the university exam they may ask a question from this section. Okay. Constraints are classified into, one is explicit constraint. Okay, what is explicit constraint means? For example, here you can note, it restricts each exercise. There is a solution vector x. Okay, in the previously discussed case, which are the value? This is a solution vector. Then which type of value it can take? This position take, that is from the solution domain. Okay, for example, b1. In the previous case, b1, b2, and these are the only values x, this position, the solution vector x and x of I can take. Okay, x of I or xi can take. So that type of constraint is called, also you can note here G1 will not come. Okay, B1 and B2 here in this way. Okay, uh, so this is called a explicit constraint. They restrict each xi to take on values from a given set. So this is G1. This is our solution domain, and these are the values we can assign to this position. Then that type of constraint is called explicit constraint. For example, if over one abstract problem, uh, which values xi can take, it will be 0 or 1. Okay. For example, this will be restriction will be like this: xi equal to 0 or xi equal to 1. Or sometimes it will be in the like in this domain. Okay, there will be a fixed domain values can take. Or sometimes the restriction will be like this: 1 less than or equal to xi less than or equal to ui, etc. Anyway, this is about the explicit constraint. Then what about the implicit constraint? The rules that determine which of the tuples in the solution space satisfies the criterion function. So I told already, there will be some constraints in the problem itself. This is implicit. The problem itself, uh, the problem has some constraint. That constraints are called implicit constraints. For example, in our case, girl should be, there should not be a girl between two boys. Okay, there should not be a girl between two boys. That is a constraint. Okay, that type of constraint in each problem is called the implicit constraint. Okay, so just note that sometimes in the university exam they may ask such a type of questions. Next we want to discuss about this control okay, general method control abstraction of backtracking approach, algorithm backtrack. Like divide and conquer, greedy, dynamic, this is the control approach for this backtracking that we can discuss in the next class. Okay, please give your attendance in the chat box. Okay. Okay, Akash. Next. Abhinand, Abhinav, Advaita. Abhinand, Abhinav, Advaita, Adarsh. Okay. Next. Sipon, Anaka, Anugra, sorry. Abhinand. Just now. Just now, personal. Okay, just now. Next. Karthika Kirtana, Pranavay Panasi, Mohammad Sina, Mohammad Ijaz, Pranavay Panasi, Pranavay Panasi.
Sir, Nafa present
Pranavay. Okay, okay. Okay. Nitin Babu. Neha present. Okay. Pranavay, Nitin Babu. Okay. Next. Raisa Khalid Rasan, Rasun, Roshan. Raisa Khalid Rasan, Nehala, Rasun, Roshan. Rasun present. Roshan Sahala B. Sahala B present. Sahala, okay. Sangeeta Saranga Sharun Sadda. Sangeeta Saranga Sharun Sadda. Sharun present. Vishnu Vaishnavi Baby Vishnu. Okay, Anjita Shirona. Okay, Sharon absent. Sharon. Okay, okay, thank you. Sharon absent.